problem I'm going to be discussing is what we call a photoelectric effect problem. And you can see it at the top here. And I'm going to walk through this with my little diagram that I've drawn here, because I find if you can come up with a visual representation for any type of word problem, it will often kind of help you wrap your head around the problem a little bit. So when the problem asks to calculate the work function or binding energy, that is the value that you see in blue. And so you notice the little question mark that I have down here. When it says that this metal has electrons being ejected with a velocity of 2.96 times 10 to the 5th meters per second, that's the part that we see in pink. So the electron is ejected and it has this velocity. And when the problem says this happens when the surface is illuminated with light having a wavelength of 550 nanometers, that's what we see in green over here. So the wavelength coming in is this 550 nanometer light. So on the left, the squiggly line, that's your light. On the right, the straight line, that's your electron being ejected with some velocity. And then this surface that we have at the bottom, that's your metal, and it has some work function or binding energy. So how do we go about solving this problem? Well, each one of these colors I have on here represents a different energy that's involved in this problem. And the very first energy I want to talk about is the energy of the light coming in. Because the photons in that light each contain the amount of energy that the wavelength of that light dictates. And we learned in class that there's an equation for this. We say the energy of the light is equal to hc over lambda, where lambda is our wavelength. And to be really, really specific about these different energies that are involved in this problem, I'm going to actually label this. Not only am I color coding it, but I'm going to label this as the energy of the light, right? So that's your hc over lambda. Now remember, this equation and pretty much all the equations we're using here are per particle equations, which means that when we plug the wavelength of the light into this equation, we're really going to be calculating the energy per photon in this light. Okay, so per particle means per photon when we're talking about light. So the other thing to keep in mind is that that photon that's coming in, that has the energy that is going to set the tone for all of the processes that are happening here. So it also represents the total available energy in the problem that we're starting with, essentially. So each photon has this amount of energy based off its wavelength, and we'll be able to calculate that with this equation. And when that photon strikes the surface, it transfers all of that energy it has into an electron in the metal. And so that electron takes all that energy and it's going to use it for two different things. One of those things is going to be the work function. It's going to pay up the amount it needs to pay, basically, to eject itself from the atom. And then if there's any energy left over, that leftover energy is going to go towards the motion of the electron, which means the speed of the electron, which means kinetic energy, essentially. So this part in pink, we can use the velocity of the electron to calculate how much kinetic energy that electron has, which again represents the amount that's left over after we've ejected the electron. And to do that, we're going to use another equation that hopefully will look familiar, either from class or maybe you've seen this in physics, right? That's this 1/2 mv squared equation. And again, I'm going to be very deliberate here about labeling the energies so we don't get confused, right? This is our kinetic energy that we're dealing with this equation. Okay, so this kinetic energy, remember, is the leftover or excess energy, and it's going to be the amount per electron that's being ejected, because it's also going to represent a per particle equation in these types of problems. Okay, so we've taken care of 2 out of the 3 of the different energies we have available here. We've talked about the energy of the light, we talked about the kinetic energy, so let's get back to this work function that we're trying to solve for. in order to understand how we're going to solve for the work function, we want to think about how these three energies are related to each other, right? I have said here that the energy of the light coming in is the total energy available, and that all of that energy is going to go towards the work function, and whatever's left over is going to be used towards the kinetic energy of the electron. So what that really means is, for any one of these situations where an electron gets ejected, the work function plus the kinetic energy should equal the energy of the light that's coming in. So I can write this out, right? So the energy of the light coming in, since that's the total amount of energy available, that gets broken down into these two components of the work function and the kinetic energy that's left over. Okay, so I can write this relationship here between these three values. And this equation can be rearranged in any way to solve for what you need to solve for. In this situation, we know what the energy of the light's going to be because we can calculate it. So we don't really want to leave it written this way because we're not trying to solve for the energy of the light, right? We're trying to solve for the work function. So if I rearrange this equation to solve for the work function is going to end up equaling the energy of the light minus the kinetic energy. And again, thinking from the standpoint of what these energies represent, right? The total energy is our energy of the light. The kinetic energy is the amount that's left over. And so if we take the amount we start with, the total energy, and we subtract the amount that's left over after we've ejected an electron, then what's left from this is going to represent the amount that was used to eject the electron, the binding energy or the work function in blue. Now, this equation that I have just written, as written, can be used in any situation where you have an electron being ejected due to light striking the metal surface. So if you know an electron's ejecting and you know that it's going to have some velocity, then you can use this relationship between these three different components of energy. But just keep in mind, right, there's nothing stopping you from rearranging this to solve for whatever value you need to solve for in a situation where the electron is being ejected, right? That is the one special condition that must be met here, is we need to have an electron ejected in order for all three of these components to exist, right? If an electron's not ejected, then we don't technically have any kinetic energy, and we're not really sure if the energy of the light coming in is actually enough to satisfy the work function. So these types of equations are very situational, right? You can only use them with certain situations, and you have to be aware of what those situations are. Let's finish this off though and solve for this actual value. So this is going to involve, if I want to use this equation down here to solve for my work function, I got to solve for my energy, my light, solve for my energy or my kinetic energy, and then I can plug those two in here to get what the work function is. So doing the energy of the light calculation, we're going to have hc over lambda. H is just going to be 6.626 times 10 to the negative 34th joules seconds. C is our speed of light, so 2.998 times 10 to the 8th meters per second. And then on the bottom, we need our wavelength, but it needs to be in meters because remember, the units that we plug in have to match the units of any constants that we have. So if I've got meters in my velocity here for my speed of light, then I need to have meters on the bottom when I plug in wavelength. So remember, you can use my trick here to convert this quickly from nanometers to meters. If you just remember that if I have a number with a prefix, I can swap out that prefix for what it stands for in the metric prefix table and keep everything else the same. So I'm going to keep the 550, and then when I get to that prefix, I'm going to put in what that prefix stands for. Now, nano stands for times 10 to the negative 9th. So I put that in for nano, and then I keep the base unit, the meters, right? So now I have a value that's in meters that I can actually plug in down here on the bottom. So 550 times 10 to the negative 9th meters. Now, if you punch all that into your calculator, you're going to get a value of 3.61 times 10 to the negative 19th joules. And from a sig fig standpoint here, let's just note that there's only two sig figs technically in this wavelength, so the 6 is my last sig fig. And let's also remember that this is the amount per photon, right? So it's a per particle amount that we just solved for there. All right, now let's switch to the kinetic energy equation. So this one was 1/2 mv squared. So 1/2. For the m, I want the mass of the electrons and the mass of the object that is moving with this velocity. And that's just a constant that I will provide for you guys. It's on this worksheet. It's also going to be on exams. And then the velocity is what we were given, the 2.96 times 10 to the 5th meters per second. But do not forget that you have to square that value. All right, so if we plug all that into the calculator, we're going to get 3.990 times 10 to the negative 20th joules. And this also is a per particle calculation, so this is per electron. Okay. Now for sig figs, our velocity has 3 sig figs, so the second 9 is my last sig fig. And for units here, let's also note something that a lot of people don't realize at this point, which is that joules actually is a special term we use for a combination of units, which is kilograms times meters squared over seconds squared. So note here, I wrote joules for my units, but when you look at the calculation, we actually have kilograms in here and we have meters per second all squared. And so that's where these units are coming from. The kilograms, the meters squared, the per second squared all come from the equation. And at some point along the road, we decided that those were kind of nasty units and we were just going to call them something special, and that's where joules comes in. Right? So when you say joules here, you're really meaning these other units. And it just is a little easier to write out than writing out this nasty expression with the units. So now that we've got our two values in joules, we can, and they're per particle values, we can plug those into this equation to get what the work function is. So my work function is going to be equal to my energy of my light, so 3.61 times 10 to the negative 19th joules, minus my kinetic energy of the electron, so 3.990 times 10 to the negative 20th joules. And remember, right, this is the per photon value, and this is the per electron value. And that makes sense also from the standpoint of, one photon transfers all its energy to one electron, right? So this process is a per particle process. Now when I punch those into my calculator, I'm going to get a value of 3.21 times 10 to the negative 19th joules. And from a sig fig standpoint, since this is a subtraction step, notice that the first value has the shortest sig figs, right, with that first decimal place. So that means my answer has my last sig fig in the first decimal place. Now this represents the joules of energy that are needed per electron, because again, these are per particle values. So this is how much energy the photon has to have in order to allow for this electron to be ejected. It has to have this minimum amount of energy. If it has more than that amount of energy, then it still will eject it, but it has to have at least this much energy. And so this value also makes sense when we come back and look at the energy of our photon. We can see that it's bigger. So it makes sense that we're ejecting an electron and that we have some energy left over for this velocity, for this kinetic energy, because the work function is less than the energy of the photons coming in.